to Europe as a Schwarzschild fellow, and yes, since then been at the AFE in Potsdam and has her own immunometer group there. And her focus is on the galactic evolution of the Milky Way and its spheroidal. Perhaps with a particular focus on the early evolution, and I'm sure she'll tell us much more now. So, please.
Thank you very much, Karen, for the introduction and also for the invitation to be here. Can everybody hear me okay? Yeah? So today I'll be talking about galactic archaeology to its limits, and I'll explain in a minute exactly what I mean with that. And so the main object of my study is the Milky Way. And of course the Milky Way as a galaxy is very interesting because we can study it in all of these details, but we cannot study external galaxies here. And in particular, I want to highlight a few things that I think are particularly unique to the study inside our own Milky Way that we cannot do elsewhere, which of course is star and planet formation, which I won't be talking much about today. The details of chemical history, which is more my field, and also stellar binarity, all of these things that we want to know to model external galaxies well, but that we can really only study in our own galaxy. So that all the information that we have about this is coming from, mainly from studies of our own galaxy and a few other galaxies in the neighborhood. So the Milky Way is not by itself, it also has this great variety of dwarf galaxies that are surrounding it. And I think these dwarfs are really interesting because they all have different stellar formation histories, they have different metallicity distributions. So really, we don't have only a Milky Way, we have this whole system of different galaxies that we can study to learn about galaxy formation in general, and then different mass scales and different types of star formation histories, etc. So what I mean with galactic archaeology is really to study present-day stars to learn about past history of the Milky Way system. And the analogy with archaeology here comes from the fact that we study something that's still here, but that was made a long time ago to understand what the conditions were at that time. So of course we don't study artifacts but stars instead, but basically we're doing the same thing. We're studying things that are still around from ancient times to learn about how conditions were at those times. This is a movie of how we think, simulation-wise, a galaxy like our Milky Way is put together. This is from the group in Durham, who simulated first a dark matter halo and then tagged it with stellar particles. And what you're looking at here are only the stars, and then run the whole simulation again. And so what you see is that it's quite a messy business, especially in the outskirts of the Milky Way, the Milky Way halo. There's lots of these tiny dwarf galaxies and building blocks that have fallen in. Here's, for instance, a particular big one that's being ripped apart by the Milky Way potential, and that will be part of our Milky Way halo. So we have all of these remnants that we can still see around us, and we see these things, these stellar streams, and these features. We see them in observations, for instance, in the Sloan Digital Sky Survey, and they can tell us something about the past of the Milky Way in a way that a galaxy like this grows. So in galactic archaeology, we like to look back in time, but of course there's a limit to this. So if we look at the history of the universe from the Big Bang all the way to the modern universe as we see it today with all the galaxies and the stars in it, then basically the limit that we can hit with galactic archaeology is about here. So this is the end of the Dark Ages, when the first stars started being born, started to assemble, started to shine their lights. Of course, these are the final relics that we can study with this kind of approach. So this is really the limit of galactic archaeology, hence the title of this talk. So these first stars are really interesting because they mark a very interesting epoch in the formation of the Milky Way. They were filling the universe with light and ionizing radiation for the first time. And this is a very nice movie called First Light by Weiss, A1, and Keller. And what you can see is that the first star formed here, which is filling the universe with its ionizing radiation. It's also the start of chemical complexity, and as such maybe also of magnetic fields and a lot of other things that we study today. There's still a lot of question marks about what were the properties of these very first stars in the universe. We're still not quite sure. Maybe they had a different mass distribution, maybe they were much more massive, and therefore maybe they had different supernova explosions at the end of their lives. And what we also don't know is their first star, the star that was formed just after these dark ages that we can still see. Is their first star still out there in our Milky Way galaxy for us to observe? That's something we haven't found one, and it's a question that we'd like to answer. So as I said, one of the challenges is how massive were these first stars. So in general, we think because the gas is hotter, because it cannot cool, and it doesn't have any metal lines to help with the cooling, we think that the gas is hotter, therefore the inflow must be larger. And in this whole formation process, the accretion disk, of course, will be larger. But then there's a question of how much fragmentation can happen in such an accretion disk. So it's the question if this all ends up into one star or if this fragments into many different pieces. So this is very much related to this question of can a true first star still be out there? Because stars, of course, their ages correlate with their mass, and in order to be formed at that epoch in the universe and still be shining today, a star needs to have a mass less than 0.8 solar masses. So only if a star was formed of that low mass at that time can we still see it out there today. This is sometimes dubbed the question of the metallicity floor. And what is meant with that is there a metallicity floor for stars of that low mass to form? In other words, do you need certain metals to cool the gas in order to form such a low mass, yes or no? And in the beginning, the simulations said that the first star would be very massive, but there's also simulations that show much more fragmentation, and occasionally some simulations form such a low mass star. So it's not ruled out that we would ever find such a star. However, nobody knows how likely this would be. If we then look at observations, so observations can really help to constrain these kind of theoretical understandings of these very early times. So this is a figure from Federal Norris 2015. It's already a little bit outdated, not so much. I've highlighted the most metal poor, in this case called iron poor, basically stars that we know of today. And two in particular I want to highlight. This is the most iron poor star that we've ever seen. It was published by Keller et al. In 2014. It's very interesting, and it has an iron metallicity of below 7. And but it's not the most metal poor thing on the plot. That actually is this one, because this one, even though it has very little iron, it has a lot of carbon and other light elements. Whereas this star has a very low iron, but also, for instance, low carbon and other things. And it's 2. So basically, this is the star that is called the most metal poor, and when it was discovered, it redefined this notion that we have of metallicity floor. At least the metallicity floor has to be so low that you can form a star like this, because we see one. And so these observations are really constraining the theories that we have. The other thing is, there's basically 2 things I want to point out in this plot. First of all, there's only a handful of stars on here, and especially at the lowest iron metallicities, we see there's really not that many. The other thing that you, of course, already have seen is that even though they're very poor in iron, they're usually very rich in carbon. So this goes up to 100, 1,000, 10,000, 100,000 times the ratio in the sun of carbon over iron. So where does this carbon come from is one of the puzzles, because we don't see this kind of behavior in stars of solar metallicity. We only see this happening at this very low metallicities. So one thing to note is that these stars are in different stages of their chemical evolution. So that means that it cannot be that they make the carbon themselves. These are not AGB stars that make a lot of carbon. So where does this high carbon come from? So one possibility is that these stars are actually the second generation, or even the third generation stars, and that this carbon actually comes from these first stars, and that they have created the carbon, put it back into the interstellar medium, and then the second generation forms with a lot of carbon. There's a few models supporting this. There's in particular a kind of supernova model, which is the faint or mixing and fallback supernovae, that kind of develops a lot of carbon into the interstellar medium. Possibly also helped by higher spin rates, because these stars have fewer metals, they're a bit more compact, and so they might have a higher spin than normal stars do. And so the very dumb picture of how this approximately works is at the end of the life of a very massive star, what you have is, I'm sure you remember from stellar evolution, what you have is this kind of onion model where the heaviest elements are in the core of the star, and then you have these different shells with lighter elements going outwards. And so the idea of this kind of faint mixing of fallback supernovae is that basically these inner layers collapse into the remnant, and the outer layers are the ones that make it out into the interstellar medium. So what you end up with is a lot of these things that are in the outer layers, for instance carbon, the lighter elements, and not a lot of the heavier elements. Like iron. So these collapse back into the remnant and are locked in. Another way that you can get a lot of carbon in a star is if it's transferred from a binary companion. So for instance, if a star is in the binary of an AGB star, and an AGB star makes a lot of carbon, and we also know that AGB stars fly on winds, so these might transfer this carbon until a different star. And the good news is that we can check this kind of thing by radio velocity monitoring. So we can see if these systems are in binaries, yes or no. So this is one thing that we try to do. This is work that we published in 2014. We have a full data set with more and more stars in preparation, and there's also some other teams who've been doing this kind of work. It's going to be by Theresa Hansen. And what you see is that if you look into these stars, and in particular the ones that show very high carbon, but also have a different chemical imprint, so low barium as well, and many of the lowest iron poor stars belong to this class, what you see is that there are some of these stars that are in binaries. So these are probability contours. On the x-axis you see the binary fraction of the population of these stars, and on the y-axis you see the typical period that they have should they be in a binary system. So you see that some of them certainly are binaries because the contours start at 20%. But what you also see is that not all of them are probably binaries, or if they are in binaries, then their periods must be really, really large. In other words, it's difficult, we cannot see if they are in binaries, so one solution is that their periods are on the order of millions and millions of years. In other words, they're not very close binaries, or that only a few of them are in binaries. If we look into stars that have high carbon but also high barium, we see very different behavior. We see that all of these stars are very likely to be binaries and also to be fairly close binaries. So these contours don't at all overlap, indicating that there's a very different formation scenario. So this is good news because it tells us that we can separate the binary stars, so the stars that get high carbon from binaries, from the stars that probably already had this high carbon at birth. So we're perhaps the second generation stars that got their carbon from the generation before. And we can do that by measuring this barium content. So the low barium stars are unlikely to be in binaries, and if they have high barium, then they're likely to be in binaries. And this makes a lot of sense, also because we think that AGB stars also make a lot of barium. So it all kind of comes together there. So a lot of these stars that I was showing before that are here in this diagram are the low binary type. So actually we think that they are the second generation kind of stars. So there's a broad picture that kind of starts to emerge, where we think that some of these stars at least belong to like the second generation or maybe third generation, but still have this imprint of these weird first stars. And what's typical for this imprint, and this is again this star by Keller in 2014, is that they have very high light elements, and then the elemental abundance increases if you go to higher and higher mass elements, as you kind of expect. But there's still many details on chemical enrichment in the early universe that are not very well understood. There's also many individual stars that don't quite fit this picture. And we see different signatures in different parts of the galaxy, which is also kind of puzzling. So there have been now a few studies, kind of pioneering studies in the inner galaxy. And if you look at all the different elements, carbon, but also other elements than carbon, you see that there it seems like these kind of low metallicity stars have a different chemical imprint. So for instance, the high carbon content that we see in the halo doesn't seem to be so present in the bulge, for instance. And we still don't quite understand what that is telling us and how that can be possible. So just to emphasize a bit on these kind of puzzles, so the other thing that we don't understand is, as I said, we cannot just look at the Milky Way, we can also look at these dwarf galaxies that surround it. And what we see is that some of these dwarf galaxies perhaps also have less carbon-rich stars. There's some work by myself and some work by Astronominal sitting here. That we have found some hints, at least, that perhaps this is the case. So perhaps there's less of these carbon-rich stars in dwarf galaxies. And so most of these carbon-rich stars that we do find are the type that are these stars that we think are the second generation kind of stars, not the binaries. And they are, a lot of the times they're found to be very, very faint dwarf galaxies. There's also hints that in the disk and in the halo, particularly in the inner and the outer halo, there's these different ratios of carbon-rich populations among the metal-poor stars. So there's quite some works now, also always on small number of stars, but that are showing more and more hints that these different environments are showing a different kind of chemical imprint of the early universe. And then, as I said, there's the problem that if we look to in the galaxy into the bulge, then we don't see this typical carbon-rich pattern that we just so nicely explained in the halo. So once we try to understand, we thought we understood everything in the halo, then we looked into the bulge and everything was different. So what we really would like is a statistical sample of these stars across all galactic environments. So from the inner galaxy to the outer galaxy, to understand how the chemical enrichment took place in these very, very early times in the universe. So here again a picture of galactic archaeology. So what we like to study is this outcome of the first stars, and we'd like to get a large sample of these, or maybe second generation, third generation stars. And we'd like to be there in the chemical evolution picture. However, of course, the problem is that there's so many billion stars in the galaxy, and how do you know which ones are these very, very old ones? And of course, we can't take a spectrum of every star in the galaxy, or at least we cannot yet. So how do you select the few stars that you are really of interest from the many stars that are out there? So one technique that has been employed is to use a prism to get some spectroscopic information for many stars at the same time. So this has been the way it's been done in the HK and the Heidelberg ESO survey since the 80s. And it's been very, very successful in finding large samples of these stars. The other thing you can try to do is use photometry, so use a combination of bands all over the spectrum to select metal-poor stars from metal-rich stars. And so one more recent development here is been using infrared bands, where you can see that you have a lot of molecular features in this infrared, and you can try and select the colors such that you don't see so many molecular bands, which means that you're probably looking at a star that doesn't have that many metals. So this works very well, but only for bright stars, because the infrared photometry doesn't go so deep. So it really only works until a magnitude 14, 15. Another technique that kind of looks a bit like the prism technique in the sense that it focuses on the same part of the spectrum is to use narrowband filters. So these graphs here show a part of the spectrum that are the calcium H and K lines. So these are two of the strongest absorption lines that you'll find in any standard spectrum. And as you can see, these lines are dependent on a few things. They're dependent on temperature, and they're dependent a lot as well on metallicity. So you see here the blue is -3, so 1,000 of solar, and the dark red are solar. So you see the lines are very, very strong in stars like the Sun, and then get quite narrow in really poor stars. So what you can do is you can design a filter that is shown here that only lets the light through in this part of the spectrum. And if you know the broadband temperature of a star, so you know how much flux you would expect from the black body spectrum in this part of the spectrum, you can then see how much flux you are missing. If you're missing a lot of flux, then it's probably a metal-rich star. If you don't lose that much flux, then it's probably a very metal-poor star. So this has been employed in the SkyMapper survey in the southern hemisphere that is positioned to do all 20,000 square degrees in the south. It's already put out its first data, internal Australian data release. That doesn't go as deep yet, but hopefully they'll get deeper. They also did some pioneering work on the bulge, which of course is very nicely reachable from the south. And there's a survey that I've been working on, it's called Pristine, in the northern hemisphere, and where we actually use this filter, which is shown here. So these are the two filters that have been used. Again, this is a spectrum of a very metal-poor star in blue, and in red you can see the filter that we use in Pristine. In gray there's the SkyMapper filter, which is a bit broader, but still it covers these two calcium H and K lines. You have to be a bit careful though, because we just saw that metal-poor stars can have a lot of carbon, really a lot of it. And so what you see, if you then look at a spectrum that has a lot of carbon, what you see here is a black spectrum, so that's exactly the same kind of star, but with a lot of carbon, and you see there's these extra features, so you have to be a bit careful that they don't leak into your narrowband signal, and that you don't confuse a star that's very carbon-rich but very iron-poor with something that is more metal-rich. So this Pristine survey is done on the Canada-France Hawaii telescope, CFHT, which is in Hawaii. And what we really do is we make it into this very efficient machine for finding the most metal-poor stars. The current footprint of our survey is about 1,000 square degrees, down to a magnitude of 21, so it goes pretty faint, which means that you can look at red giant stars all the way to the end of the galactic halo. And just to give you an impression for how efficient this is, we do about 100-second integration per square degree, so it's really, really fast. And so there's many people, some of them in the audience, who are part of this survey, particularly in France and Canada, some people in Germany and in Spain. So the 1,000 degrees footprint that we have looks a bit like this. We have a few extra things in our footprint. One is a couple of Milky Way satellites that we find very interesting to study as well. And there's the Bootes satellites, Bootes 1 and 2. This is Palomar 14's globular cluster. Here's Hercules. There's Palomar 5, which is a globular cluster that has a tidal stream, which is shown here in this orange line. And this is M5. What we also have in our footprint is all of the slow broadband photometry, which is very useful for us to understand the temperatures of the stars, but also the spectroscopy from the Segway, the slow Segway survey, which is very useful for us to calibrate ourselves against. And this is what this kind of calibration looks like. So as I said, what we do is we use the broadband colors from slow to get some dependence on temperature. So basically, this is the temperature axis. And then here we use a combination of broadband and this new Castle-Rich K information on the y-axis. And so what I've plotted here are all the stars that are overlapping with Segway. So these are stars that do have a spectrum, and they're color-coded by the metallicity of that spectrum. So what you see is a beautiful rainbow-like figure, which means that this new filter is very metallicity sensitive. And you can see that the stars that are around -3 are nicely lined up here. The lines that you see are not actually fits to the data, they are what we get if we do the same exercise for synthetic models. So they are predictions from synthetic models about where the stars should lie, and the colors are where they actually end up. So this plot actually looks already pretty good, but we can do even a bit better. Through a combination of band stars, we can clean ourselves of a lot of variable stars. We also do some color cuts to get rid of white dwarfs, and what you get then is this right panel, where you see that a lot of stars here, which we don't think belong there, are cleaned away, and it looks even a lot cleaner there. I should say that the black line here is where we expect stars to fall that don't have any metals. So they are free of any metals. And of course, we'd like to find some stars of that property. Our metallicity scale works pretty well. We have an RMS scatter of 0.2 dex all the way down from 0.5 to -3. So this again is the Segway metallicity for these stars. This is the metallicity that we would derive from photometry. You see it's pretty nicely one-to-one with a bit of scatter, as you expect. If you compare that, what you can do from broadband colors alone, they also have some metallicity sensitivity, but it's not as good, and it also kind of loses its sensitivity at the metallicity around -2. So it's very difficult for broadband colors to really distinguish things below that metallicity. Whereas from our narrowband colors, we can actually make that distinction. So it's a much better precision, and also the number here corresponds to the number of stars that we could use. So to use broadband metallicities, you have to make some color cuts, so it means that you only end up with a small selection of the sample. So really, with this kind of technique, what you're doing is you're opening up a new machine that was before only accessible to spectroscopy, and you're now getting photometric metallicity with the help of this new narrowband photometry. Our completeness of selecting stars below -3 is about 84%, which means that we end up with a lot of stars, and we don't have a lot of stars that don't make it into our cuts that we think should be interesting. Even more important, perhaps, the success rate of uncovering stars with -3, if we compare it to the Segway sample again, is in the 26% range. And just to compare this, it might not sound that impressive, but if you compare that to past and ongoing surveys, they had about a 3 to 4% success rate, so it's pretty good. And then of the remaining 74%, 80% is still very poor below -2. So even though 26% is below -3, really high percentage of that is still below -2, so they're not really contamination. They're just a bit more metal rich than we're aiming for. Only 50% is really contamination in the sense that they are higher than -2 in metallicity. We're also doing some spectroscopic follow-up, and from this we can tentatively confirm that these percentages are achievable from our spectroscopic results. These are some images from the spectra that we took at the ICP telescope. These stars are selected to have similar temperatures, but their metallicities change a bit from -2 to -3.3. And what you see that is in particular the Galactic K line gets smaller and smaller if you go to lower metallicities. So these are the kind of spectra at medium resolution that we then take to follow up our results. Also from these spectra we can measure, for instance, the carbon content of these stars. So from our full sample of spectra that we now have, we found about 13% to be below -3. Not all stars that we followed up we expect it to be below -3. If we only look at the 49 candidates that we really thought from the photometry were below -3, we actually have a 33% success rate, which again is close to what I just estimated from the second metallicities. And we derive metallicities from the very applied mapping by our colleagues in Dwarf. We also have a high resolution follow-up program at CFHD Astronominal, and that's really to check the individual analysis to really study these stars in more and more detail. And this is also some work that we have in preparation. So the number of targets that we expect from such a survey, so we expect about 10 stars per square degree below a magnitude of 18, which means that these kind of surveys are also very suited for the new generations of multi-object spectrographs like we do for most, because we can give them, like, if they can spare 10 fibers per square degree, we can give them the most interesting metaphor stars to look at, so that's a pretty good deal. And it will give us a homogeneous follow-up of full metaphor sample, including an estimate for the alpha elements, for instance, this carbon enhancement, and also different neutral capture elements, which would be really, really interesting. And if we can learn a lesson from the past, if you look into the HK and the 100 ESA surveys, what becomes clear is that the 100 ESA survey goes just a little bit deeper, a magnitude deeper, than the HK survey, but it had a much higher percentage of metaphor stars. So I really think the more you probe out into the halo, the more you find these interesting first generation, second generation stars. So really going fainter means opening up discovery space. And of course, these kind of studies have always been quite local. We've always looked at very bright stars that we can study in detail. So it's really interesting for me to really go faint and explore the whole galaxy instead of just the tiny part of it that are sunless. Just to make sure that we can also find these ultra-metaphor stars, of which I showed in the beginning we only know about 10 up till now. So we can actually also find these ultra-metaphor stars. We followed put a few fields, especially on these stars, and they fall just above this -3 line in our footprint. So we know that we are well positioned to also find these stars that tell us the stories of what we do in the universe. Now to switch a little bit here, I'm going to talk about what we find in simulations. We try to, when we started the survey, we try to understand what it is that we expect in the different environments in the Milky Way. So for this, we're using the Apostle simulations, which is a suite of 12 local groups in very high resolution, N-body plus full hydrogen arrays. And what you find from these type of simulations is basically what you expect is that there are more old stars in the halo than in the inner galaxy, and there are also more metaphor stars in the halo than in the inner galaxy, which is what we already know because we know the halo to be quite old metaphor component, whereas the disk of the galaxy, of course, is much more young and metal rich. But if you then look into a single metaphor stars and you find, for instance, in the halo or in the inner galaxy, what you find is there might be more metaphor and old stars in the halo. There might be more metaphor stars in the halo, but not all of them are old, because the gas never gets very enriched in that part. Some of the oldest metaphor stars sink to the center of the galaxy. So if you discover a metaphor star in the inner galaxy, it's very likely to be old. And this is demonstrated here in this figure on the right. This is the radius inside the galaxy, so from the inner galaxy to the outer galaxy. And this is for all the stars that are metaphor. This gives you the fraction that is old. In this case, old is older than 0.8 billion years since the Big Bang. And so what you find, even though we saw before that the absolute number of, the fraction of older and metaphor stars goes up in the halo, then if you look at the stars that are metaphor, the fraction that is old actually goes up in the galaxy. And this can be explained because in the inner galaxy, the chemical evolution is very rapid. So that means that in the beginning there were these metal poor stars that were formed, but they were quickly followed up by more metal-rich younger populations. So there were no young metal poor stars there, whereas in the halo, that is the case, that there are metal poor stars that are younger. And this is actually, it's not a completely new result. This was already shown in some other simulations. For instance, this is a famous graph of Tomlinson, 2010. What it shows here is the percentage of stars with -3 or lower that formed prior to a redshift of 15 in his simulation. And what you also see is that these numbers go up in the inner galaxy and they go down in the outer galaxy. However, when we were looking at our hydrodynamical simulation, we did notice that the exact numbers that are given here, the quantitative results, depend heavily on the way that you treat metal mixing in your simulation. So we had a couple of different options to choose from in this hydrodynamic simulation, and what we found is that depending on which way you treat your metal mixing, this trend is very steep or actually a lot shallow. There's always a trend there, but it's sometimes very steep and sometimes very shallow. So I think actually we need observations to tackle this and to tell then the theorists about how to treat their metal mixing, because it's very difficult from the simulations alone to tell what exactly the quantitative result here is. So what we see, if we look into detail in the simulations, these are some examples for some of the halos that we see. On the left you see just a density map of stars. On the right you then see a pixelized map of the same galaxy, which is colored by the percentage of old stars among the metal poor population. So here we select all the metal poor stars, and the color here shows what a fraction of them are old. So you see that indeed in the center it's always a bit darker. There's always more of these old stars in the center. We can also see very dark patches in the outskirts. So actually we find that a lot of these dwarf galaxies, there's also these very, very old stars there. And if you compare, and this is one of the different halos, if you then compare these maps one by one, what you see is that if you find a dark patch here, it almost always corresponds to a little dwarf galaxy. So we see that also in these dwarf galaxies, the percentage of old stars, these really stars that are tracing the very early chemical evolution, can be quite high. So dwarf galaxies are very good to hunt for these oldest stars. If we again look at the fraction of stars that are old in the metal poor population, we find that they can range basically from 0 to 1. Some of them are very, very interesting grounds for these oldest stars. They are also very interesting systems by themselves. And especially we'd like to understand basically the outskirts of these dwarf galaxies, to understand their dynamics. There's some people here in Heidelberg like to work on the cold dark matter content of these dwarf galaxies. Are the most dark matter dominated things in the universe? Yes or no? We'd like to understand that they are stripped by the Milky Way, how much they are disturbed by the tidal influence of the Milky Way, etc. So there's all kinds of reasons to study these dwarf galaxies. First of all, there would be these very, very interesting old stars, but also these are interesting systems in themselves to understand a bit more about chemical evolution and dynamical evolution in the Milky Way system. So this is also something you can do with the kind of metallicity sensitive information that we get out of a survey of like Pristine. So it's not just that you can use this kind of metallicity sensitive information to look for the oldest, most metal poor stars. What you can also do is make slices of different metallicities of the halo. Because it's photometry, you get every star basically that is out there. So we played this game a little bit, and on the bottom panel, what you can see is there are several known substructures that you very, very easily recover. For instance, here there's a Buddhist dwarf galaxy. If you make a metal poor cut in the halo stars, you see it popping out very, very well. Initially, I wasn't aware that number 14 was in the footprint. I discovered it, only to find that it was already discovered many, many years ago. So you can see it here. This is a red pixel showing a very, very overdense region here, and kind of moderate metallicity. So you can also use this kind of metallicity sensitive information to kind of make slices in the metallicity space and use this as another way of understanding the Milky Way halo and substructure. So in the top panel I'm showing this famous image from the slow digital sky survey, where we see all of the different streams that we see in this part of the Milky Way. So this is the Sagittarius stream, there's the Orphan stream right here, there's a couple of dwarf galaxies, so the coloring here is by distance. And this is where most of the pristine footprint is right now. So we have part of the Sagittarius stream in, but we're not quite overrun by it. Then we have part of the Orphan stream, part of the Heidelberg 5 stream, which is this tiny little thing down here. So we have all these kind of substructures that we can study with this kind of information as well. And in particular, this kind of information can also help you to select stars in these dwarf galaxies and to study the systems. Also to study the dynamics of these kind of systems. So this again is the Bootes dwarf galaxy. And this is an ordinary color magnitude diagram. So G minus I color here, G magnitude here. And this is what the Bootes galaxy would look like, so an isochrone that fits this kind of galaxy. So you might think that all the stars that are colored in black here are stars that belong to this dwarf galaxy. So you might, if you're doing a spectroscopic survey, you might want to put like a fiber on all of these stars, or a slit, or take a spectrum of some kind for all of these stars. The things that have circled in red are stars that are followed up in the studies by Norris et al. And Kaprizov et al. That were actually found to be members of this dwarf galaxy. So they surveyed about, 400 stars each, and they found a couple of really good members. Now on the right, I've done the same kind of color plot that is this metallicity that then covers the different metallicities, like we've seen before, that you can do with Pristine, with this calculated information. And what you see is that the stars that are black, the full-moon isochrones, are everywhere. But the stars that are circled red are particularly in this upper part of the diagram. So these are the stars, of course, because this dwarf galaxy is very pure. So you can actually select this part of the diagram and do a much more efficient spectroscopic follow-up of the dwarf galaxy like this. You don't have to survey 400 stars to find 10 members, especially in the outskirts. You can be much more efficient if you have this information beforehand. This is another illustration of the same thing, going much fainter. This is a very faint dwarf galaxy that's very recently discovered, Triangulum II. This is what happens if you do a CMD selection of all candidates. You see that there's something there, but it's only very small, and there's all of these other members, possible members, that you have to get spectra for. However, if you also use metallicity information, you clean up this kind of space much better. What you see is that the dwarf galaxy is still there in the middle, but what you see is that you don't have all of these different possible member candidates anymore in the outskirts. So you can be much more efficient in your spectroscopic follow-up, and you don't need to do 10 pointings, you only need to do 1 pointing. So we also have a special dwarf galaxy program with Pristine. We had already 11 of them observed, a bit deeper than we do our normal footprint in 2016A, and we have 12 scheduled for this year. So this brings me to my conclusions. I think it's very exciting to map the Pristine Universe. I hope I convince you that the oldest and most metaphor stars, they really inform us of the early buildup of galaxies and first stars physics. With radio pulse monitoring, we can understand the nature of these kind of stars. So we think from there that some of these stars show the blueprint of first star chemical enrichment, which is pretty exciting, bringing us all the way back to this the special epoch in galaxy evolution. This metallicity decomposition that we can do with Pristine is very powerful from near-infrared photometry. Of course, this also goes for Starkenburg in the south. It's really efficient to uncover the rare, extremely metaphor population of stars. and we're starting to follow them up with spectroscopy to learn more about them, is really an added dimension to Milky Way deconstruction, even in the era of Gaia. So what we'll end up with is 60 velocities plus metallicity information, which I think can be pretty powerful. And it also helps, as I was showing in the last few slides, by studying these faintest dwarf galaxies, by eliminating foreground contamination of the Milky Way itself. It's much more metal rich. If we look into the latest hydrodynamical simulations of chemical groups, what we find and predict is that all the stars are in a galaxy, as has been predicted before, but we also show that the halo is a very interesting hunting ground for these stars, and in particular, these small dwarf galaxies can be very interesting candidates. And be careful, because quantitative predictions of this kind are really dependent on the way that you treat metal mixing in these kind of simulations. I'll stop there. Thank you very much. So of course they're calcium lines, so they are more connected with the calcium abundance usually than with the iron abundance. We use it as a proxy for overall metallicity. The reason for that is a bit twofold. One of the lines have very strong rings, which are actually dependent on metallicity in general, because they are dependent on the radiation pressure, and so they do follow the overall metallicity of the star, but also because in general, so the comparison sample that we use to calibrate against is usually better constrained in iron than it is in calcium. And because in most stars, these two vary in lockstep, you can get one from the other. But indeed, you're right, if the calcium is very different from the iron, as happens in some of these metal-core stars, so for instance, we saw this star at -7 in iron. It's actually, I believe, -5 in calcium. Yeah. So there you would see it as -5, not as -7. But then you would get a first metallicity estimate from that, and then you would follow up with the spectrum and get exactly the right abundances.
But what is carbon hence us? Carbon defines the overall metallicity.
So carbon will define the overall metallicity, that's right. So in our narrow band spectrum, we don't have that many carbon features, so we will be mostly dominated by the strength of the calcium HK and not by the carbon. So for us, a star that has a similar calcium but a very different carbon will look more or less similar. And it's slightly different for a skymapper, where they have a bit more carbon features. And so there, a star that has high carbon will look a bit more metal rich in their calibration. It's true.
Have you checked quantitatively whether these very strongly carbon enhanced particles can interfere with your selection? Because they look redder in the both band colors, therefore you should get some contamination.
Right. So we did, I'm not entirely sure from the top of my head how carbon enriched the two stars are that we checked. I think they're moderately carbon enhanced. So there we do at least find them in our extremely metal-core sample, so we would pick them out and get spectroscopy for them. So that's one check. For really the ones that have carbon over iron of +5, I'm not sure.
I have two questions. You have been pointing to the metal mixing prescription.
Yes.
What is the main agent, so to say, that drives the mixing? Is it the supernova story, or what is the thing behind it?
So in this, so I think there's two possible answers to this. So what we checked specifically in the simulation is what you can do in this hydrodynamical scheme is either you take the metallicity of the gas particle to be transformed in the metallicity of the stars that form out of that gas particle. Or the other prescription that is used is to use some kind of kernel to also consider the metallicity of the particles surrounding it in order to get the metallicity for the star. So that is what's going on the level, say, of what you really do in the simulation. So those are the two different prescriptions that we tried. And then, of course, if you go to a semi-analytic approach, what most people do is they assume everything to be mixed perfectly within a galaxy. So that's another extreme. So there's the extreme from some semi-analytical prescription which find a very strong gradient. And then there is, if you don't use any mixing, you find a very flat gradient. So probably the truth is somewhere in between. So all that we're saying right now is we can't really say quantitatively what this gradient should be, just to be careful and to not put too much faith in these kind of quantitative descriptions. I think the physical mechanism behind it would indeed be supernova feedback or any other wind mixing that you can think of.
The second question is a simple one. The pristine data, they are not publicly
No.
Right? Are you planning to make this stuff public?
Not in the near future, because we will explore it a bit more ourselves. But yes, probably in a few years from now we are. But not directly.
Follow-up question on the metal mixing.
Yeah.
So you do not treat the explicit mixing of metals in the pH position, right?
We do, so there is some mixing going on. So but we store both the case where we don't do any mixing, and we store the case where there is some mixing. So the difference I was showing is the same simulation with the mixing turned on and the mixing turned off. So both of the cases are stored in the memory.
Your diagram of the color has your HK metallicity diagnostic. It's a two-fold question. First, are the colors really a precise diagnostic of the effective temperature? Because you probably assume that low metallicities start generally become slightly lower anyway. Or
Yes.
could you not see that in the diagram?
So that's exactly why we try to calibrate ourselves on the Segway sample, because it's an empirical calibration. So all of these kind of effects should be in there as well, because these are real stars for which we know the metallicity from the spectra. But what we see is that actually they agree very well with what we expect from synthetic spectra. One thing I haven't talked about that goes a bit into the equation is stellar gravities. So they do have a slight effect on the lines. It's not so big, fortunately, at low metallicity, which means that low metallicity this works very, very beautifully. But then at higher metallicities, the giants and the dwarfs do show a slightly different sequence. Still, the effect is not as big as the metallicity sequences, but there is a bit of an effect there. Yes.
Following up on that, you were covering the lowest metallicities rather well for the blue part of the diagram, basically. But it didn't seem you were really getting a lot of very metal poor or extremely metal poor stars on the cool end. Is that
Yes.
just a range effect because you're not probing for cool dwarfs? Or
No, we are.
Is the HK feature becoming less useful?
No, actually it's a lot if we can both. So in this kind of diagram, you see. So basically, this whole line is where we look for metal poor stars. So this is basically the tip of the RGBs. These are pretty cool stars. This is where the turn-off is at the lowest metallicity. So basically, we're not looking at BHB stars because they are a bit of a mess. We're not looking at the really, really cool stuff because that's pretty messy there as well. But we're basically reaching the temperature range from the turn-off to the tip of the red giant range. And of course, the main sequence that has the same temperature range as well. So both giants and dwarfs and hotter and cooler stars, we all probe that. And actually you see that at the cooler parts, these lines get further apart, so it actually works a little bit better. But there's fewer stars there, just because of stellar evolution.
Okay, I have a final question. Well, first of all, the Keller star has not limited calcium at -7 as well.
Okay.
The detection is at -7. The upper limit to iron is at -7. Roughly is -6. So that is discrepancy. I just refresh my memory about that. I want to ask you, what do you think? Have we really learned something so far about the IMF of stars, in the sense that there's so many free parameters in the supernova yield models, especially these fallback mixing type models? They have, well, there's the mass of the stars, there's the explosion energy of the star, and there's the amount of mixing and fallback. And if you take all of these things into account, you can fit the few abundances that we can derive for these stars with mass, essentially. So how do you think more statistics is going to help here?
I do think more statistics, in the sense that right now it's in the regime where you're allowed basically to take one star and fit it, and then take the next star and fit it. Of course, if you start to have a statistical sample of 100 of stars, it's very unrealistic to start and do that unless you have a good physical reason. I think it becomes more realistic to then have to develop a model that kind of accounts for the population rather than for one star here and one star there. And the other thing I think that could help I think the most constraining thing on the IMF is if we find actually a star that is still primordial, in the sense that it basically only has hydrogen and helium and whatever it picks up from these. I mean, that will be the real test, right? I mean, if we find hundreds of these stars and not one of them has that signature, then it has to mean that they're all dead, and then basically, so they were hydrogen. I think that's probably the most robust test. But I think also in the supernova in this case, it will be, at some point, if you have a statistical sample, it will be very unlikely if you need to design a special kind of supernova for every star. You will have to come up